Hi, we are the University of Southampton Pegasus Free Rover team, a group of 6 students working to build and improve our third generation rover. I'm looking forward to go back and compete at the 2019 URC.
We were the first UK team to qualify and compete at the University Rover Challenge. Building on that experience, we have changed the rover to improve its performance and comply with the new URC requirements.
For the extreme retrieval and delivery missions, traversing through rough terrain and steep slopes is fundamental. Based upon last year's design and experience at the competition, this year we've decided to work on a number of changes.
The team focused on achieving a substantial mass reduction while increasing the system reliability. This was done by changing the suspension and the chassis design.
In order to increase stability, the team has increased the rover's track width and wheelbase, as well as the robot's clearance from the ground. These changes allow the rover to traverse steeper slopes and more challenging terrain. The newly implemented differential bar system transmits motion from one side of the suspension to the other in order to maximize wheel contact with the ground. Last year's plate suspension has been replaced with one constructed from carbon fiber tubes and graphite reinforced nylon SLS 3D printed inserts. These provide the suspension with the required strength and flexibility needed while achieving a considerable mass reduction. To ensure that the carbon fiber tube suspension was a suitable choice, a compression test was performed in a servo-hydraulic machine. This year's chassis is constructed out of lightweight welded aluminium cross-section. In order to reduce traction losses, the team has implemented a direct drive system, which also provides higher torque. In order to complete the extreme retrieval mission, the rover will use its 5 degree of freedom robotic arm, which is capable of lifting payloads of up to 6.5 kilograms at maximum extension. Flexible rubber on the gripper's fingers provides additional friction. The robotic arm is also used in the equipment servicing mission. The cameras attached to the robotic arm allow for accurate and precise movement of the end effector, which allows manipulation of knobs, buttons, drawers, and keyboards.
Delivering a stable and reliable electronic system that integrates a newly designed science package and allows for autonomous and teleoperation control is the focus for this year.
To complete the teleoperation missions, the rover is wirelessly networked with the base station via two 2.4 GHz antennas. A maximum range of between 700 and 1,000 meters has been determined during testing, depending on terrain. Control commands are sent to the rover computer, which relays them to the rover control unit. The rover control unit controls actuators and motors while reading signals from sensors and transmitting the data to the rover main computer. Where possible, groups of sensors and circuits are localized on custom PCBs.
For the science task, we have built a camera vision system which uses the reflectance properties of the elements to identify potential life on rock and soil samples.
The science system is attached to the end of the robotic arm. 12 pairs of LEDs that emit light, ranging from ultraviolet to infrared, are used to illuminate the samples. These are mounted on a PCB that is connected to a microcontroller. Spectral graphs are obtained from data that is acquired by a calibrated CMOS sensor which detects UV, visible and infrared light. A flexible foam enclosure allows us to image in completely dark conditions, regardless of terrain, and to accurately detect the light reflected from the sample. Once acquired, pictures are transmitted to the base station for analysis. These are used to generate a reflectance spectrum graph for each pixel in the image. To identify which compounds are present, results are compared to a database of the spectra of bio and geomarkers commonly used as life detectors, such as sulfates, carbonates, and chlorophyll. The characteristics of these compounds will allow us to detect if life is extant, extinct, or neither.
For autonomous navigation, we have developed new ways to detect and avoid undesirable terrain, while also improving the range and accuracy of the tennis ball detector.
A new system to create an obstacle map from elevation data and aerial images has been developed, giving the rover the ability to minimize traversal time over rough terrain without having to build a map during teleoperation. A far more robust tennis ball detector allows the rover to be resilient to noise and ensure that a tennis ball has been located at ranges of up to 10 meters from the rover using a method based on multi-scale template matching. GPS, rotary encoders, an inertial measurement unit, and a Connect V2 sensor provide input to an extended Kalman filter, allowing the rover to predict its location with a reduced impact from sensor drift. Similarly to last year, The rover will be tested in the Airbus Mars yard. Thanks for watching, and we hope to see you at the URC.